So we've been talking about plastic behavior of beams and frames, right, and looking at collapse mechanisms and things like that. When it comes to torsion, we have to go back to our stress strain curve, right? And so we're going to kind of go back to that initial concept that where we introduced the idea of plastic behavior. But now we're just going to do it in the context of torsion. So we'll consider a solid circular shaft that is made of a ductile material. And so the idealized stress strain curve, again, right, would look something like this. And of course, that's not very realistic. Later on in the lecture, we have a more realistic view of it. So if we are considering the case of pure torsion, then our Moore's circle will be perfectly centered on the origin, right? Where we would have over here, right, a principal stress equal to max torsion, right? This would really be our max torsion point, right? Pure torsion. And then our principal stresses would be the same magnitude as the maximum shear stress. All right, so this would be our second principal stress over here. And so this is, again, for the case of pure torsion. So if we think back to the Tresca criteria versus the von Mises criteria, let's see what comes from that. And this, let's see, this first chunk of the lecture, it's not really essential for the rest of the lecture notes, but it's just, I threw it in there to kind of tie us back into the concept of our failure theories and whatnot. So for the Tresca criteria, we have the difference between the two extreme principal stresses divided by 2, and we set that equal to the half of the maximum, the limiting value that we choose, right? And so in the past, we chose that limiting value as the yield stress, the stress that will initiate yielding of the material. So we'll stick to that in this lecture as well. So we'll say this is going to be equal to our maximum shear stress minus negative tau max over 2. And we'll set that equal to the yield stress divided by 2, right? And that's basically what this is right here, the tau y. So we get that our maximum shear stress in the material is 0.5 times the yield stress, and that's when failure occurs according to the Tresca criteria for this case. With a von Mises application, we would implement that long equation that uses the stress of distortion, right? And that's going to be 1 over the square root of 2 times 6. And the maximum shear stress squared is what that equation would reduce to. And then the square root of that, set that equal to our limiting value. And so then we would obtain that yield stress is equal to square root of 6 over square root of 2 times tau max, or tau max is equal to 0.577 times the yield stress. All right, so here's another scenario, right? The case of pure torsion on a circular shaft, or I guess it doesn't really matter in this case, the shape of the shaft. But for the case of pure torsion, we get different values for defining failure according to these two approaches. Now, the corresponding torque that is tied to the onset of yield all right, to get that, we'll relate our yield stress to the torque that's associated with it. So that's just applying our relationship between torque and shear stress. So that's torque times the radius divided by the polar moment of inertia. All right, and we can write the yield torque is equal to pi over 2 times the yield stress times r cubed. And this version would specifically be for circular cross sections. After plugging in the appropriate expression for the polar moment of inertia. And I will further specify solid circular cross sections for this. All right, so then the corresponding angle of twist, we would call that phi at the onset of yield, or phi y, would be the yield torque times the length divided by shear modulus g and the polar moment of inertia, or the yield stress times the length divided by shear modulus and the radius. Stress distribution over the cross section, right? We'd have zero stress at the center of twist, and then it would increase to a maximum value of that yield torque, or yield shear stress. And that is all associated with the yield torque. This, of course, is a cross-section view. All right, so now recall the shear strain for torsion, all right? So in general, gamma is the symbol that we use for shear strain. And it doesn't matter if it's torsion or otherwise. But specifically for torsion, that looks like, if we have something like this, all right, with a torque applied, that twist will cause a given line on the undeformed shape to do something like that, right? Where the angle, the total angle of twist, which we've been calling phi in this class, will be greatest at the free end, right? And it will be equal to 0 at the fixed end. So this is the shear strain gamma, right? That angle. So on the previous page, we just defined the angle of twist associated with the onset of yield and drew the stress distribution that's associated with that state. If we continue to apply torque or increase the torque beyond that point, then the yielding of the material will advance beyond the outer fibers. All right, so we're going to define what I call the yield front radius, which is this RY showing up in the sketch here. So I'll say here the yielding of the material advances to a radius RY. Right, where that yield radius is always less than the outer radius, capital R, and has the associated stress distribution shown over here, which I will sketch now. So we would have our yield stress constant at that yield value in the portion that has yielded, and then beyond that, a linear decrease to 0. Oh, it doesn't want to be linear for me today. There we go. Linear decrease to 0 at the center of twist. And this torque is greater than the yield torque. So if we apply the geometric relationship between the total angle of twist phi and the shear strain gamma, that's why I drew the sketch for gamma up above to refresh your memory on that. We have phi times variable radius r is equal to gamma times the length. So let's see, VR, yeah. So at the yield front, we have phi times that radius to the yield front is equal to the yield strain times the length, which is equal to the yield stress times the length over the shear modulus G. So we can say that the yield radius is equal to the yield angle of twist divided by variable angle of twist times the outer radius r. So this represents just the relationship between the yield radius, Ry, and the angle of twist. And this is based on this specific condition, right, where the angle of twist is greater than the yield the onset of yield angle of twist, and the torque is greater than the onset of yield torque. So I'll just note for that. This is for phi greater than the yield phi and torque greater than the yield torque. And I think my notes maybe were mistaken. I'm pretty sure this is supposed to be over here, the total radius, phi r gamma L. Or no, I guess that it was right the way I had it. I was overthinking it. So yeah. All right, any questions so far? Okay. All right, so in order to get the torque, we will integrate the shear stress distribution, right, as usual. So total torque is equal to 2 pi times the integral from 0 to the yield front, Ry, of the yield stress. So first we're looking at, right, this portion of the stress distribution. So that would be the yield stress times the variable R divided by the yield front times our variable R and our variable R dr to get our total right, force times moment arm in that expression. And then for the rest of the distribution, this guy right here, we have 2 pi times the integral from Ry to capital R, which represents the outer radius, of the shear stress tau y times variable R times R for the moment arm, and dr to complete the area over which that shear stress is acting. So from that integral, we obtain torque is equal to 4/3 times the yield torque. And then in brackets, we have 1 minus 1/4 times the ratio of the yield angle of twist to the variable yield angle of variable angle of twist. That ratio is cubed. All right, so this equation right here, we'll box it up, is applicable for a solid circular cross-section and for the condition where the yield angle is less than the angle of twist and the yield torque is less than the applied torque. All right, so I can tell you now that in your homework, the one that I haven't posted yet, that will be your last homework assignment, but I will post it probably this afternoon. It'll be due Friday after break. The problem associated with this lecture, you will have a hollow circular shaft. So this equation will not apply, but you'll get a similar equation for the hollow circular shaft. And I provide some extra information to help guide you to that end, right?
Is our relation of R sub y, that yield front radius.
Mm-hmm.
Is that true for only solid circular cross sections, or?
No, so that is valid for hollow circular cross sections as well. The difference that is going to affect this result is that, let's say, all right, so let's just say your hollow section, right, this part was hollow, right? For this portion, right, for that portion within the hollow section, your stress distribution would still, it would still be a linear relationship to a 0 point here, but there just wouldn't be any material there to experience that stress. So you wouldn't be integrating from 0 to Ry, you would be integrating from the inner radius to Ry.
Okay.
Yeah. Yeah.
And I wouldn't imagine that these are valid for like a square or something like that.
We'll talk about other sections later. Yeah, but yeah, that's correct. This approach wouldn't apply to other shapes. In general, like the general relationship or the general behavior would be similar, but since it's not a circular shape, right?
A little different.
Yeah. So, yeah, good question. All right, so now we are at the point where, okay, if we continue to increase that torque until the entire cross-section has yielded, then we've reached the ultimate condition, right, the ultimate state. So the ultimate torque that the shaft can support will be associated with that yield radius approaching 0, all right? So the entire cross-section has yielded, so that yield radius doesn't exist anymore. And if we look at our relationship above between the yield radius and the angle of twist, that means our angle of twist is approaching infinity. And then from the previous equation for torque, as the angle of twist approaches infinity, the associated torque, which would be the ultimate torque, would be 4/3 of the yield torque, right? So that's the limit of this equation as phi approaches infinity. And the stress distribution associated with that state would simply be a constant magnitude of the yield stress. And of course, that ultimate torque is greater than the yield torque. All right, so now let's think about twisting this shaft to an angle that is 2 times the yield, the initial onset of yield angle, right? And determining the condition of the shaft at that point and the stress distribution. So here now we are looking at a little bit more realistic stress strain curve where it's not perfectly linear after the onset of yield, right? There's a yield region and then you're in that plastic zone. And this is also not a perfect stress strain relationship, right? Not totally realistic, but more realistic than before. So here's that yield angle phi y associated with initial yield, and then our ultimate torque is represented by that final point there. So we're looking for an angle that is 2 times our yield angle, so that would be something like this. So at that angle, we would have our yield front radius equal to r over 2. All right, so I'll note that is r over 2. Our stress distribution all right, we'd have our yield stress up here, and then linear to 0. Wow, it's really liking these cubic functions. All right, make that linear to 0. All right, so we want to determine the torque associated with this state, right? So I'm going to come down here actually to calculate that. So we would have our torque is equal to 4/3 times the yield torque. And then in parentheses, we had that 1 minus, or in brackets, 1 minus 1/4 times the yield angle divided by the angle that we are considering, right? The angle for our state, which is 2 phi y cubed. All right, and so this value in brackets comes out to be 31 over 32, if you run that math. And that gives us a torque of 1.292 times the yield torque. All right, so that's our torque there. All right, so we've twisted it to this point. The angle of twist has doubled from the initial point of yield. And then if we consider removing that torque, that force, the material will respond elastically, all right? So we have an elastic unload. So let's think about that process and figure out what our residual stress state will be. Because there will be residual stresses, right? Because we've yielded it into the plastic region, so there will be some permanent deformation associated with that. So the unload stress is linear with a value of 0 at the center of twist. So we'll use the elastic equation for unloading from this point. So our unloading stress we would have torque times radius divided by polar moment of inertia. So our maximum shear stress would be 1.292 times the yield torque times the radius divided by polar moment of inertia, which is equal to 1.292 times the yield stress. So the residual stress state that corresponds to a torque of 0 represents a complete unloading, right? We'll superimpose the loading and unloading stress states. All right, so our loaded stress state right, we add our yield stress in that region. Our torque is equal to 1.292 times the yield torque, and our angle of twist is 2 times the yield angle. Our unloading stress try to draw this a little bit to scale. All right, we have 1.292 times the yield stress, maximum at the outer fibers, and 0, right? It's a linear unload. We had 0 at R equals 0. And here the unload torque is also 1.292 times the yield torque. So superimposing these two states, we have a torque of 0, and our net shear stress distribution will leave us with 0.292 times the yield stress at the outer fiber. And then at the final yield front, right, the point where yielding had just occurred when we started unloading, that value will be 0.354 times the yield stress. Draw that. Zoom in. And we'll have 0 at the center of twist. So it's going to look like this. within the cross section. So I have these notes already in there. I'll give you a minute to write them down for yourself, but our maximum residual stress is that 0.354 that occurred at half the outer radius, which was our yield stress for phi equals 2 phi y. And that is after just one cycle of applying that torque to that point and then removing it. Questions?
Is the max residual stress always gonna be at the interface between the plastic area and the, no, I guess the yielded, hasn't yielded?
That's a good question. I think, let's see. I wonder, it may depend on where that yield front, how far that yield front reached. I haven't investigated that, but that would be an interesting little case study. All right, because this value would depend on where that point is, and yeah, that would be a good investigation. Good question. All right, so now that leads us to the more fun part about plastic torsion, which is the sandhill analogy. So we just went through this process for circular cross sections, right? The sandhill analogy is the method that you would apply to anything else that's not a circular cross section. And recall from our previous lectures on torsion, if you have an arbitrary shape, right, we use that membrane theory where you have an inflated membrane over the cross section, and the total torque is equal to 2 times the volume under that membrane, and the slopes of that outer surface of the membrane are equal to the shear stresses directly below. So the maximum shear stresses occur at the outer edge, and we'll now just take that to the level of ultimate twist. So if we have a shaft that has an arbitrary cross-section, so say for an arbitrary cross-section shape, if we twist it until we've reached that yield stress throughout, all right, for ultimate failure, then the membrane slope all right, recall the slope of the membrane is equal to the shear stress directly below. So the slope of the membrane at ultimate failure will be equal to the yield stress at every single point, right? So that reduces to basically a pyramid shape with a base that is consistent with your arbitrary cross-section. And so say the membrane slope is equal to tau y at all locations, including the outer edge. So this is what we call the sandhill analogy, because it represents a sandhill that is poured onto the shaft cross-section. So you had a circular cross-section, right? You'd have a cone. With a slope as such. So the yield stress would be equal to, right, that's your height, radius r. Yield stress would be equal to h over r, or h is equal to shear stress times capital R. All right, and that's shown down here as well for a circular cross-section. So the torque associated with that condition, or let's see, yeah, we'll get there. All right, so remember from the previous page, I think actually the first page of this set of notes, we had the yield torque for a circular cross-section was equal to pi over 2 times r cubed times the yield stress. So our yield stress is equal to 2 times the yield torque over pi r cubed. So let's check this. What I'm doing right here actually is, right, we're using a circular cross-section, so I'm using the sandhill analogy to verify that it works with the circular cross-section since we already derived those results. So volume of the cone is 1/3 times pi r squared h. So let's see if that is equal to half of the ultimate torque. All right, ultimate torque is equal to 2 times the volume, which is 2/3 pi r cubed times the yield torque, which simplifies to 4/3 times,
torque is stress.
yeah, this one is yield stress. Thank you, I misspoke. That simplifies to 4/3 times the yield torque, and that checks with the solution that we obtained on page 2. All right, I know we're out of time. I don't want to keep you too late, so we just have a few more minutes to wrap up these thoughts, and I'll just start with that on Friday. But basically, we just demonstrated that this is valid because it works for a circular cross-section, and if it works for a circular cross-section, we can apply it to other cross-section shapes. So I'll just point that out next time. All right.